In the previous chapter, we learned that experimental research provides the most powerful design for the testing non-methodic causal hypotheses. This chapter examines experimental methodology in more detail. You'll learn to distinguish different types of experimental designs, which include true experiments and quasi-experiments, as well as to evaluate the utility of particular designs for reaching causally valid conclusions, to identify problems of generalizability with experiments, and to consider ethical problems in the experimentation. We will also return to the relationship between prison security level and inmate misconduct later in the chapter. True experiments play two critical roles in criminological research. First, they are the best research design for testing causal hypotheses. Even when conditions preclude the use of a true experimental design, many research designs can be improved by adding experimental components. Second is true experiments provide a comparison point for evaluating the ability of the other research designs to achieve causally valid results. Experimentation has always been a key method of scientific research. A famous experiment, perhaps the first, was conducted by Archimedes in 230 BC when he tested the way in which levers balance weights. In 1607, Galileo conducted experiments by dropping weights to test the theory of falling bodies, and by mid-1800s, the use of experiments in the rapidly growing fields of scientific research was well established. While many think that experiments remain in the domains of physics or psychology, experimental methods are being increasingly used in all social science research. Recall from previous chapters that a true experiment is an experiment in which subjects are assigned randomly to an experimental group that receives a treatment or other manipulation of the independent variable, and a comparison group that does not receive the treatment or receives some other manipulation. Outcomes are measured in a post-test. True experiments have at least three things. Two comparison groups, one receiving the experimental condition and the other receiving no treatment or intervention, or another form of experimental condition. Random assignment to the two or more comparison groups. Assessment of change in the dependent variable for both groups after the experimental condition has been received. The combination of these features permits us to have a much greater confidence in the validity of causal conclusions than is possible with other research designs. As you learned in Chapter 6, two more features further enhance our confidence in the validity of the experiment's findings, which include identification of the causal mechanism and control over the context of an experiment. True experiments must have at least one experimental group and at least one control, some kind of comparison group. The experimental group is a group of subjects that receives treatment or experimental manipulation, and the control or comparison group is the group of subjects who are either exposed to a different treatment than the experimental group or one that receives no treatment at all. The control group differs from the experimental group by one or more independent variables whose effects are being tested. In other words, the difference between the two groups is that the experimental group receives a treatment or condition we're interested in, whereas the comparison group does not. In many experiments, the independent variable indicates the presence or absence of something, such as receiving a treatment program or not receiving it. Treatment is the manipulation that exposes subjects in an experiment to a particular value of the independent variable, which takes us here to the pre-test and post-test measures. Matching is another procedure that's sometimes used to equate experimental and comparison groups, but it's a poor substitution for randomization. Matching of an individual's in a treatment group with those in a comparison group might involve pairing persons on the basis of similarities such as age, gender, year in school, or some other characteristic. The basic problem is that, as a practical matter, individuals can only be matched on a few characteristics. Unmatched differences between the experimental and comparison groups may still influence outcomes. However, matching combined with randomization can reduce the possibility of differences due to chance. Matching is a procedure for equating the characteristics of individuals in different comparison groups in an experiment. It can be done either individually or an aggregate basis. For individual matching, individuals who are similar in terms of key characteristics are paired prior to the assignment, and then each member of each pair is assigned to a different group. For aggregate matching, groups are chosen for comparison that are similar in terms of the distribution of key characteristics. All true experiments have a post-test, that is, the measurement of the outcome in both groups after the experimental group has received treatment. True experiments also have pre-tests that measure the dependent variable prior to the experimental intervention. The post-test measurement of an outcome or a dependent variable after an experimental intervention or after a presumed independent variable has changed for some other reason. The pretest measures of an outcome or a dependent variable prior to an experimental intervention or change in a presumed independent variable for some other reason. The pretest is exactly the same test as the post-test, but is administered at a different time. An experiment may have multiple post-tests and perhaps even multiple pre-tests. Multiple post-tests can identify when the treatment has its effect and for how long. And it's an important part for treatments that are delivered over time. Sometimes referred to randomization. A random assignment is what makes the comparison group in a true experiment such a powerful tool for identifying the effects of treatment. If subjects are randomly assigned to either the experimental group or comparison group, the researcher can assume that the only difference between the two is that the experimental group received a treatment or intervention and the comparison group did not. Before and after designs. It's a quasi-experimental design that may consist of before and after comparisons of the experimental group, but it does not have a control group. The common feature of this is the absence of a comparison group. All cases are exposed to only the experimental treatment. The basis for comparison is provided by the treatment measures in the experimental group. These designs are useful for studies of interventions that are experienced by virtually every element in some population. The simplest type of before and after design is the fixed sample panel design. So this fixed sample panel design is a longitudinal study in which data is collected from the same individuals, the panel, at two or more points in time. In another type of panel design, panel members who are replaced with new members. The ex post facto control group design is a design in which the treatment and comparison groups are designated after the treatment is administered in an ex post facto or after the fact control group. The design perhaps should be considered non-experimental rather than quasi-experimental because the comparison groups may not be comparable to the treatment group. The mechanism is a discernible process that creates a causal connection between two variables. So let's examine how well quasi-experiments meet the criteria for identifying a non-lythetic cause. Association between the hypothesized independent and dependent variables, time order of effects on one variables on the others, and non-spurious relationships between variables. In experiments ability for causal internal validity, an experiment's ability to yield valid conclusions about causal effects is determined by the comparability of its experimental and control groups or comparison groups. The causal effect is the finding that change in one variable leads to change in another, which is the ceteris paribus, or other things being equal, that we've previously discussed. There are 5 basic sources of internal validity. Selection bias, which characteristics of the experimental and comparison group subjects differ. Endogenous change, when the subjects develop or change during the experiment as part of an ongoing process or independent of the experiment treatment. External events or history effects, which when something occurs during the experiment other than the treatment that influences outcome scores. And then contamination, when either the experimental group or the comparison group is aware of the other group. and it is influenced in the post-test as a result. And then we have treatment misidentification, when a variation in the independent variable or treatment is associated with variation in the observed outcome, but the change occurs through a process that the researcher has not identified. Selection bias, which is here on this slide, is you may already realize that the composition of the experimental and comparison groups in a true experiment is unlikely to be affected by their difference. If it were affected, it was cause selection bias. Even when the random assignment plan works, the groups can differ over time because of differential attrition, or what can be thought of as deselection. This is the groups become different because, for various reasons, subjects are more likely to drop out of one group than the other. Differential attrition is a problem that occurs in experiments when comparison groups are likely to drop out one over the other for various reasons. Endogenous change is the type of problem that's considered to be an endogenous change occurs when natural developments in the subjects independent of the experimental treatment account for some or all of the observed changes between pretest and post-test. As such, an endogenous change is a major problem with quasi-experimental designs, particularly before and after designs. This is a source of causal validity that occurs when natural developments or changes in the subjects account for some of the observed change between pre and post-test. There's 3 specific threats to internal validity for endogenous change testing. So we're taking the pre-test. It can influence itself post-test scores. Subjects may learn something or be sensitized to an issue by the pre-test, and so now their views or responses may differ on the post-test because of that. Maturation, changes in outcomes or scores due to the lengthy treatment period that may be due to maturation. Subjects maturing, age, they gain experience, school, and more knowledge. And then regression effect, people experience cyclical or episodic changes that result in different post-test scores. This is called a regression effect, a source of causal invalidity that occurs when subjects are chosen for a study because of their extreme scores on the dependent variable and become less extreme on the post-test due to the natural cyclical or episodic change in the variable. External events, sometimes referred to as the history effect during the experiment. Things that happen outside the experiment can also change the subject's outcome scores. Casual conclusions can be invalid in true experiments because of the influence of external events, but not every experiment is affected by them. The specific features of an experiment must be considered carefully to evaluate the possibility of problems due to the external events. For example, in an experiment in which subjects go to a particular location for the treatment and the control group subjects do not. Something at the location unrelated to the treatment could influence the experimental subjects. Validity contamination occurs in an experiment when the comparison group is in some way affected or affects the treatment group. This problem basically arises from failure to adequately control the conditions of the experiment. When comparison group members become aware that they're being denied some advantage, they may increase their efforts to compensate, creating a problem called compensatory rivalry, or the John Henry effect. This John Henry effect is a type of contamination in experimental and quasi-experimental designs that occurs when control group members are aware that they're being denied some advantage and increase their efforts by way of compensation. On the other hand, comparison group members may experience demoralization if they feel that they've been left out of some valuable treatment and may perform worse than they would have outside the experiment. The treatment may seem, in comparison, to have had a more beneficial effect than it actually did. Treatment misidentification occurs when the treatment itself does not cause the outcome, but does cause some intervening process. the researcher is not aware of and has not identified. This term can also refer to unknown contaminants or consequences for subjects in the control group that have to do with the experimental manipulation. Treatment misidentification has at least three sources: expectancies of the experimental staff, which can also be known as the self-fulfilling prophecy, which is a source of treatment misidentification in experiments and quasi-experiments that occurs when change among experimental subjects is due to the positive expectancies of the staff who are delivering the treatment, rather than the treatment itself. Also called the self-fulfilling prophecy, can be minimized with the following: a double-blind procedure. This is an experimental method in which neither subjects nor the staff delivering experimental treatments know which subjects are getting treatment and who's receiving the placebo effect. The placebo effect is a source of treatment misidentification that can occur when subjects receive a treatment that they consider likely to be beneficial and improve because of that expectation rather than the treatment itself. The Hawthorne effect is a type of contamination in an experimental and quasi-experimental designs that occurs when members of the treatment group change in terms of the dependent variable, because their participation in the study makes them feel special. To avoid treatment misidentification, field researchers are now using process analysis more often than in the past. This is a research design in which periodic measures are taken to determine whether a treatment is being delivered as planned, usually in a field experiment. Generalizability is the need to generalize findings. This can be thought of as the Achilles heel of the true experimental design. The design components that are essential for a true experiment and that minimizes the threats to causal internal validity make it more difficult to achieve sample generalizability, which is the ability to apply the findings to a clearly defined larger population. In contrast, cross-population generalizability is no more or less achievable with experiments than with other research designs. Sample generalizability exists when a conclusion based on a sample or a subset of a larger population holds true for that population. For example, Sherman et al. In 1992 found that arrest reduced repeat offenses for a sample of offenders in Minneapolis. If this finding is assumed to be true for all misdemeanor assaults that occurred in Minneapolis, researchers could say that their sample results were generalizable to the entire population of Minneapolis. Factorial survey design is embeds the features of true experiments into a survey design in order to maximize generalizability. In the most common type of factorial survey, respondents are asked for their likely responses to one or more vignettes about hypothetical situations. The content of these vignettes is varied randomly among survey respondents so as to create the quote-unquote treatment groups that differ in terms of particular variables reflected in the vignettes. Interaction of testing and treatment is another threat to both external and internal validity, and occurs when a pre-test sensitizes the individuals in an experiment to a particular issue or influences them in some way. I will talk about that on the next slide. So researchers sometimes deliberately take advantage of the interaction of testing and treatment to increase external validity. One design for doing so is the Solomon 4-group design, which randomly assigns subjects to at least 2 experimental groups and at least 2 comparison groups. This is a common part of the testing and treatment process. It's another threat to both internal and external validity, which occurs when a pretest and sensitizes the individuals in an experiment to a particular issue or influences them in some way. And so the Solomon 4-group design is something that they can deliberately take advantage of. Social science experiments often raise difficult ethical issues. Deception, which is used in social experiments to create a more realistic treatment, often within the confines of a laboratory. We have to follow the ASA Code of Ethics. This allows deception when it's unlikely to cause harm, when it's necessary for the research and it's followed by adequate explanation after the experiment is over. The selective distribution of benefits is an ethical issue about how researchers can influence the benefits subjects receive as part of the treatment being studied in a field experiment.